All right, so today we are going to continue talking about power analysis of steady-state sinusoidal circuits. The first thing that we are going to talk about today is effective values of periodic signals. Now, an effective value is something that some of us have been using without really knowing what it is or what it means. So we're going to look at that first. By bringing in some practical stuff into this class, right? So what I am going to attempt to draw here is a standard outlet or receptacle that's used here in the United States. Please bear with my terrible drawing skills. Okay. So we might see something like this where we have a large slot, smaller slot, and then something in the middle here like this. It's kind of half circled shape. So this is trying to be your standard wall outlet here in the US. And in this particular system, this large slot is for what's called the neutral wire. The smaller slot is for what's called the hot wire. And the semicircular slot is connected to your ground wire. So when you plug something in, it is receiving a voltage measured between the hot and the neutral wire. Positive polarity on the hot wire, negative polarity on the neutral wire. So the question that I want to ask of you guys is, what voltage is supplied by an outlet here in the United States?
Is it 24 volts?
It is not.
12?
Don't we have 110?
So you might hear it as 110, 115. Typically speaking, it's somewhere in the ballpark of 120. So I'm going to write 120 here. So let me ask you a slightly different question. Is electricity distributed as AC voltages or DC voltages here in the United States?
From the power plant to our houses, it's AC, but then when it goes into our devices, it's DC?
So from the power plant to our houses, it is AC. To our devices, some of our devices, let me prefix this, it is converted from AC to DC using what's called a rectifier. But that is very device specific. So for instance, in our computers and things like that, the power supply for our computers converts that 120 volts AC into 5 volts DC. For some other things, it might be 12 volts DC or 9 volts DC. But for a lot of things, that AC voltage isn't converted at all. So microwaves run off of AC power. Our lights and ceiling fans, washers and dryers and ovens, refrigerators, all of that kind of stuff runs off of AC power. In fact, if it doesn't involve the use of transistors specifically, the overwhelming majority of the devices will run off of AC power. So this 120 volts or 110 or 115, it's all really the same thing. What does that represent? Is that the magnitude of the AC voltage? Well, not exactly, okay? So that 120 volts is what's called an RMS voltage. And we'll talk a little bit about what RMS means here in a moment when we're deriving things. But effectively, it is a shorthand notation for the following voltage signal. V of t, a time varying voltage, which is what we would expect for an AC system, would be somewhere in the ballpark of, let me get my calculator out here to give you a more specific number. Sorry. What I thought, 169.706 cosine. So the United States operates at a linear frequency of 60 hertz. So 60 times 2 pi is going to be 120 pi t plus some phase angle that depends on when we start measuring our voltage signal, volts. Now, this representation is what we would see if we connected an oscilloscope to an output so that we could literally measure the voltage as a function of time. It contains a lot of information, but not all of it is needed in a lot of circumstances. So instead, electrical engineers represent this voltage with an effective value, and that effective value is this 120 volts RMS that we are, or some of us are familiar with. So let me explain to you what an effective value is. So an effective value for a periodic signal is a DC representation of the signal that delivers the same amount of average power to an arbitrary load. So if we plug in, let's say, a microwave to an outlet, it will receive some amount of average power during its regular operation. If we connected it to a 120 volt DC source, it would absorb the exact same amount of average power. Okay. So let's say that our arbitrary load is a resistance. Okay. The average power that our resistance would receive from a periodic voltage waveform would be given by 1 over t times the integral over 1 period of our periodic voltage waveform squared divided by our resistance value. So this is nothing more than a little bit rewritten version of our instantaneous power relationship. We integrate that instantaneous power over 1 period and then divide by the duration of the period to get the average power. Okay, so that's what it would look like for a periodic waveform V of t. For a DC waveform, our average power is simply given by our DC voltage squared divided by R, the relationship that we learned on the third day of class. So what I'm going to do is I'm going to set these two average powers equal to each other and solve for VDC. That's what's going to give me my effective voltage for my periodic waveform. Okay, so let's do that over on the right-hand side of the screen here. So I'm going to say that VDC squared divided by R, my average power in a DC circuit, is equal to 1 over the period times the integral over 1 period of my periodic voltage waveform squared divided by R, and I'm integrating with respect to time. So average power is equal to average power. One thing I can notice is that both sides have a factor of 1 over R, and since the resistance doesn't change, this bit cancels out. Okay, so the value of the resistance that is absorbing the power is not necessary. So now to get VDC, I simply need to take the square root of both sides. So our DC voltage, and I'm going to call this now V effective because this is the relationship for effective values, will be the square root of 1 over t, so 1 over the period, times the integral over 1 period of our periodic voltage waveform squared with respect to time. Okay. So what this mathematical operation is we're taking the square root, R, of the arithmetic mean or average, so that's M, of the square S of the voltage signal. So we get the RMS voltage by carrying out this operation. We can do something similar for currents, right? So if we have a periodic current waveform, much like you guys had in your homework 22, problem 4 or 5, I don't remember which one off the top of my head, but it's the last problem that we looked at in yesterday's class meeting. The average power would be 1 over t times the integral over 1 period of the square of our current waveform times our resistance in a DC circuit. The average power is simply the square of our DC current times the resistance. Putting these two expressions equal to each other, we get IDC squared times R is equal to 1 over t times the integral from 0 to t of I squared times R. And once again, we have a common factor of R, so they cancel each other out. Taking the square root of both sides leaves me with the effective value for my periodic current is equal to the square root of 1 over t times the integral from 0 to t of I squared dt. So it's effectively the exact same relationship, but this time we're squaring the current. And this gives us the RMS value of a current. Okay. Try and square that off there. All right, so let's put this expression into practice for a few examples of periodic waveforms. Okay. So let's say that I have a function. Let's make it a voltage function just for the sake of argument. And it is a positive rectangular pulse like so, followed by a negative rectangular pulse, and then it's off. And then this repeats over and over again, so that we have a periodic function, right? Let's make this 8 volts, make this -2 volts. How could we describe our voltage V of t? To me, this looks like a piecewise function, right? So it looks like it's 8 volts over the interval from 0 less than t less than, let's make this 2, this 4, and this 5, 2 seconds. It looks like -2 volts from the interval 2 seconds is less than t is less than 4 seconds. And it looks like 0 volts over the interval 4 seconds is less than t is less than 5 seconds before it repeats this over and over and over, right? So this is what our voltage waveform looks like over one period. So if we wanted to find the effective value of this periodic voltage waveform, we would use the equation above, where our effective voltage is going to be 1 over the period times the integral over one period of our voltage squared with respect to time, and then we take square root of this whole thing. Right? So what is the period of my function?
Uh, 0 to 5.
All right, so the period is 5 seconds. I agree with that. Then I'm going to integrate. So my first interval is from 0 to 2 seconds. So I'm going to integrate from 0 to 2 seconds. My voltage is 8 volts. So I need my voltage squared. So that's going to be 8 volts squared dt. My second interval is from 2 seconds to 4 seconds. The value of my voltage is -2 volts squared dt. And then my third interval is from 4 seconds to 5 seconds. The value of my voltage is 0 volts. Let's square it, dt. I'll close my brackets and extend this square root sign. So I'm integrating over one period from 0 seconds all the way out to 5 seconds. But I've broken this into 3 integrals, excuse me, because the voltage has 3 discrete values over this interval. All right, so from here, it's just simple math, right? So we're going to have 1 over 5 seconds. So what's the integral of 8 volts squared from 0 to 2 seconds? So the 8 volts is a constant. So if I square it, I'm going to have 64 volts squared. And now I just have the integral from 0 to 2 seconds of dt. Well, the integral of dt is just t. So 2 seconds minus 0 seconds is going to look like 2 seconds. So 64 volts squared times 2 seconds Then I'm going to have negative 2 volts squared, which is going to look like positive 4 volts squared. Four seconds minus 2 seconds is 2 seconds. Then I'm going to have 0 volts squared, which is going to look like 0 volts squared. 5 seconds minus 4 seconds is 1 second. So obviously this last term is just 0. So 64 plus, sorry, let's see here. Come on down. 1 over 5 seconds. So 64 times 2 is 128. Plus 4 times 2. I get 136 volt squared seconds. This second cancels this second, leaving me with the square root of 136 over 5 volts squared. And that is going to be 5.215 volts RMS. So we use the units volts RMS to indicate that we are using or have come up with an effective value. So that way we can differentiate this between a true DC signal here. So if we look at our waveform here, does it make sense that the effective value is 5.215 volts? That's kind of a hard question to answer, right? Realistically, we would expect it to be somewhere between its maximum value and its minimum value, but the duration it spends at these points is also important. So to me, this seems like a fairly reasonable guess here, right? So effectively what this means, or what we've done here, is we've said that this periodic signal delivers the exact same amount of power as this DC signal. Okay. Let's look at something a little different. Let's make this one a current this time, just for the sake of argument. So let's say that our current is a series of triangular pulses, right? We might call this a sawtooth wave. This peak value, let's call it 10 amps. And let's say that this thing repeats every 4 seconds. How would we describe this current signal? Mathematically.
Um, 10 over 4
All
over
right.
2.
So 10 over 4 is 2.5.
2.5 over 2, so 0.5.
Why over 2?
Because I'm calculating it like a triangle, like I'm dividing out the half of the triangle.
I'm not calculating the area or anything. So if I'm trying to describe this line, I want to use the slope intercept format because this is a straight line that's increasing linearly, right?
Right.
So the slope is definitely 10/4, which is 2.5, and I'm going to call this amps per second. I'm going to multiply that by time, and then my intercept in this case is 0, so I'm going to leave it alone, right? So this is what our current waveform looks like over one period, where I'm just choosing to look at the period from 0 to 4 seconds so that I don't have to apply any time shifting to this thing, right? So if I want to find the effective value of this current waveform, I effective is going to be the square root of 1/t times the integral from 0 to t of I squared with respect to time. What's the period of this function?
Four seconds.
Exactly right. It repeats itself every 4 seconds. So I'm going to have 1/4 seconds times the integral from 0 to 4 seconds of 2.5 amps per second times time measured in seconds squared dt. Let's see, 2.5 squared. I'm going to pull some constant terms out here to make our life a little bit easier. So we're going to have 1/4 seconds is already outside of the integral. I can pull that slope out, but I need to remember to square it because of this guy right here. So 2.5 times 2.5 is 6.25, if my mental math is right. Yep. And I'm going to have amps squared per seconds squared as my units. Now I have the integral from 0 to 4 seconds of just t squared. So what's the integral of t squared?
T to the 3/3.
Yep. So let's pull my factor of 1/3 out. So I'm going to have 1/3 times 1/4 seconds times 6.25 amps squared per second squared. And then over here, I'm going to have t cubed evaluated at 4 seconds and 0 seconds. So let's do some things here. So square root of 6.25 divided by 12 amps squared per seconds cubed. Just combining all of my units and all that kind of stuff together. 4 seconds cubed, so 16 times 4 is 64. Seconds cubed minus 0 seconds cubed. 6.25 times 64 over 12. Looks like 33 1/3 or 100/3. And my units are going to be, square root of that. Amp squared because my seconds cancel each other out. So square root of 100/3, 5.774 amps RMS. So it really doesn't matter what type of waveform we have, voltage or current. The only thing that we need to know for sure is that it is a periodic function. If it is a periodic function, we can find the effective value of it by simply applying our RMS equation, where we take the root of the mean or average of the square of the function. Okay. So we did two arbitrary periodic signals here. Let's do one last signal. It's going to be a voltage for the sake of argument. And let's say that it is a sinusoidal voltage of the form Vm cosine omega t plus some phase angle theta v. So to find our effective voltage, we would have the square root of 1 over t times the integral from 0 to t of v squared dt. What's my period here? Anybody remember the relationship between the period of a sinusoidal signal and the angular frequency of a sinusoidal signal? Something that we talked about in our review of sinusoids.
1 over the omega, the W.
So t isn't going to be 1 over omega, although it's pretty close. T is equal to 1 over f, our linear frequency. And omega is equal to 2 pi times f. So if I'm not mistaken, we should have 2 pi over omega here, which you guys had to use this relationship in a couple of your different homework assignments and all that kind of stuff. So with our period equal to 2 pi over omega, let's substitute that in here. Okay. So 1 over the period is going to look like omega over 2 pi. Then we're going to integrate from 0 to 2 pi over omega. And now I'm going to square this voltage waveform, right? So I'm going to use the trig identity. Let me do it in blue. Cosine alpha times cosine beta is equal to 1/2 cosine alpha minus beta plus 1/2 cosine alpha plus beta. This is the trig identity that we used yesterday when we were multiplying sinusoidal functions together. But here, alpha and beta are the same thing. So I'm going to have 1/2 times my magnitude squared times cosine of 0, which is 1, plus 1/2 of my magnitude squared times the cosine of twice alpha. So 2 omega t plus 2 theta v, close this off, dt. Much like I did yesterday when we were finding the average power, I'm going to break this up into two integrals. So we're going to have omega over 2 pi times the integral, break this up, 0 to 2 pi over omega of 1/2 Vm squared dt plus the integral from 0 to 2 pi over omega of 1/2 Vm squared cosine twice omega t plus twice theta v dt, close brackets, extend this out. So let's look at this bit right here. So I'm going to plot this thing just really quickly. I wanted this to be black. For the sake of argument, let's make v of t a cosine function with a phase angle of 0, right? So it would be something like this. So this red dot represents v of t. This purple thing is going to be this bit right here, which I'm just going to call this PAC of t just so that I have a label for it. It's oscillating at twice the frequency, right? So it might look something like this. I'm integrating over one period of my voltage waveform here, which means my limits of integration are going to stretch from here all the way out to here. This is exactly 2 periods of this signal PAC, right? So we discussed this in class yesterday, but what is the integral of any sinusoidal function over an integer number of periods? So what is this area plus this area plus this area minus this area minus this area?
Is that the generic equation we started out with?
No, what is it? What are those areas added together? I'm looking for a number.
Oh, 0.
Yep, 0. Anytime I integrate a sinusoidal function over an integer number of periods, I will get 0. So this whole term is just 0. So if we look at what we have going on right here, well, the 1/2 and the VM squared are literally just constants. So I'm going to wind up getting, let's do it down here, the square root of omega over 2 pi times 1/2 VM squared times the integral from 0 to 2 pi over omega of dt. Well, the integral from 0 to 2 pi over omega of dt is just 2 pi over omega, which means this integral just cancels out this fraction, and we're left with an effective value of the magnitude of the voltage divided by the square root of 2. So I want to point out a couple of things here, okay? The effective value of a sinusoidal function, it does not matter if it is a sine function or a cosine function, is simply the magnitude of the sinusoid divided by the square root of 2. This result is independent of frequency and it is independent of phase angle, which means it does not matter at what frequency our sinusoid oscillates, and it does not matter at what phase angle we start our measurements. Why this is so impactful is because here in the United States, where we operate at a linear frequency of 60 hertz, we can find the effective value of our sinusoidal voltages and currents in our steady state systems by simply taking the magnitude of the sinusoid and dividing by √2. If instead we went over to Europe, where they operate at a frequency of 50 hertz, we can find the effective values of our voltages and currents simply by, or for sinusoidal signals, simply by taking the magnitude and dividing by the square root of 2. So it does not matter where we are in the world, literally, the effective value is the same thing, okay? Magnitude over √2. So we don't have to do special rules for designing in different regions if we're dealing with effective values for sinusoidal signals. Okay. All right. So now let's talk about complex power. So the complex power is really something that electrical engineers made up. Okay. It is a way to look at power in a steady state sinusoidal circuit that takes into account both the average power, which is exactly what we talked about in class yesterday, as well as the contribution of energy storage elements, and kind of bundles everything together in a succinct little package that contains a ton of information, okay? So I want us to look at our relationship for average power that we came up with in class yesterday. 1/2 the magnitude of the voltage times the magnitude of the current times the cosine theta V minus theta I, okay? This was the equation that we came up with for average power yesterday for a generic network. What I'm going to do is I'm going to split up that factor of 1/2, okay? So I could call it Vm over the square root of 2 times Im over the square root of 2 times the cosine of theta V minus theta I. And Vm over the square root of 2 is just the effective value of a sinusoidal voltage. Im over the square root of 2 is just the effective value of a sinusoidal current times the cosine, again, of theta V minus theta I. So we have an expression for our average power now in terms of our effective values. Now, what somebody much smarter than me came up with was they recognized that this is just the real part of the following complex operation. V, I'm going to put a squiggle over it here, and we're going to talk about this in a moment, times I with a squiggle over it, conjugate. So let's talk very briefly here about this squiggle notation, as I'm calling it, all right? So if we have a voltage signal, a sinusoidal voltage signal of the form Vm cosine omega t plus theta v. And similarly, we had the current waveform of the form Im cosine omega t plus theta I. What would the frequency domain representation of these signals be? So what would our phasor voltage V be?
VM.
That's part of it.
VM angle theta.
Yep. So VM angle theta V. And similarly, we would have I is equal to Im angle theta I, right? So we have our time domain representation here. And here we have our frequency domain representation. Well, there is another domain that we can work in, and this is where complex power relation, this is the domain that complex power relationships are used in, and it's called the RMS frequency domain. So if I have an RMS phasor voltage V, that is nothing more than my phasor voltage V divided by the square root of 2, which is going to be Vm angle theta V divided by root 2, or V effective with an angle of theta V. And I can do the same thing for my current, right? So I phasor divided by root 2 is going to look like Im angle theta I divided by root 2, or I effective angle theta I. Okay. Call this the RMS phasor domain. And it is the exact same thing as the frequency domain, except that we're using effective values for voltages and currents. Okay, same thing. What it does is effectively get rid of this factor of 1/2 that keeps cropping up. That's really all it does. Okay. So the average power using RMS phasor quantities is simply the real part of the operation where we multiply the RMS phasor voltage by the complex conjugate of the RMS phasor current. That operation is what's known as the complex power. Okay, so we're going to start with a definition here. S, I'm putting a bar over this because it is a complex number, is going to be equal to the RMS phasor voltage V times the complex conjugate of the RMS phasor current I. So let's talk units here. So whenever I multiply voltage and current, what are my expected units?
Resistance. Wait, no, power.
So what are the units of power?
Watts.
Watts. Okay. So complex power is not measured in watts, right? So I'm going to put an arrow here. I'm going to give this a name. Complex power. And complex power is measured in volt amperes, okay, or VA. The reason why complex power is measured in volt amperes is because we don't want to confuse it with average power, which is measured in watts, okay? So dimensionally, they are literally the exact same thing, but we made up a unit so that electrical engineers could distinguish between the different parts of what we are talking about, okay? So complex power is measured in volt amperes. So if you buy a generator or a UPS, an uninterruptible power supply for a computer or something like that, it will typically have two ratings on it. One of them will be measured in watts and the other one will be measured in volt amperes, because it is trying to tell you what the average power and the complex power ratings for that particular device are. We'll talk about the distinctions between those two quantities here in a moment. Okay, so complex power S is measured in volt amperes. Since this is a complex number, we can represent it in rectangular form or polar form. So we're going to start with our rectangular form, okay? So the rectangular form is going to be the real part. So that's going to be the magnitude of our RMS phasor voltage times the magnitude of our RMS phasor current times the cosine of theta V minus theta I. And by the way, this magnitude here is nothing more than V effective, and this magnitude here is nothing more than I effective, so that we get V effective, I effective, cosine theta V minus theta I. That's the real part, plus J, magnitude of the voltage, magnitude of the current, sine theta V minus theta I. This bit right here is the average power. It is literally the exact same thing that we were dealing with in class yesterday. Typically, we give this quantity the symbol P. Okay? We might include a subscript AVG, but generally speaking, I'm just going to leave it as P. The average power is measured in watts, W, which is the unit of power that prior to today we had used for everything. Okay. The imaginary part here is what's known as the reactive power. It's typically given the symbol Q. Reactive power is measured in volts, or volt amperes. Put the plural too early. Reactive, or VARs. So our complex power is simply the sum of our average power and our reactive power. Okay, so let's talk about things here very briefly. The average power is the portion of the complex power that is capable of performing mechanical work. Okay, so effectively, it's the portion of the complex power that gets converted into heat by a resistance. Okay. The reactive power is the portion of the complex power that gets sent back and forth between the source and the load. So it represents energy storage in the system. We will not have any reactive power in a system unless there are energy storage elements like capacitors and inductors. Okay. So since the reactive power just represents power getting sent back and forth between the source and the load, well, why is it important? So without our utility grid having some temporary energy storage in it, anytime we experienced a surge in usage, so for instance, when everybody gets home at 5 and starts cooking dinner at the same time, we would have blackouts because there would be no energy storage to help accommodate that increase in demand, okay? So while the reactive power represents no net transfer of energy, it is critically important to the infrastructure of all industrialized nations, okay? All right, so here we have the rectangular portion. I've hit you with, I guess, 3 equations right now. We'll make things a little less awful here in just a moment. But before we get to that point, I'm going to make things even worse by introducing a few more, okay? So in polar form, our complex power, let me write this here, S is equal to V times I conjugate, will be given as the magnitude of S with an angle of theta S. Or let me back things out here. The magnitude of the voltage of theta V minus theta I. Okay. This quantity right here is what's known as the apparent power. Its symbol, as it were, is the magnitude of S because it is literally just the magnitude of the complex power. And because complex power is measured in volt amperes, apparent power must also be measured in volt amperes because it is literally just the magnitude of that complex number. This phase angle, theta V minus theta I, is what is commonly known as the power factor angle. And we call this theta S, okay? And because it's an angle, it's obviously measured in degrees or radians. So let me box some things up here, right? So we have this relationship for complex power, this relationship for average power, this relationship for reactive power, this relationship for apparent power, and this relationship for power factor angle. So 1, 2, 3, 4, 5 equations. This seems like help you guys figure out what's going on here, and effectively make you never need to use any equation but this one by introducing a simple visual diagram of what's going on. And this is what's called the power triangle. So for an inductive load, where Z is going to equal to R plus J X So just meaning that we have inductance and not capacitance. Our power triangle is going to look something like this. Okay. So this is going to be our positive imaginary axis. This is going to be our positive real axis. Our complex power S, let's put it in purple here. Is here. The projection of S onto the real axis is our average power. The projection of S onto our imaginary axis is our reactive power. The length of this vector S is our apparent, and the angle formed between our complex power and the positive real axis is theta S, our power factor angle. So in summary, S, which is simply the product of RMS phasor voltage times RMS phasor current, is equal to P plus JQ in rectangular coordinates and apparent power angle, power factor angle in polar coordinates. The reason why I'm pointing it out in this way is because if you know how to use your calculator and you can remember which part is which, you never need to use this equation or this equation or this equation or this equation. The only equation that you will need to actually use is this one right here. So let's put this into practice.
So sorry, there is a slight delay with what I'm seeing on your tablet. The only one we'll need is the S bar equals V tilde I tilde conjugate.
Yeah.
Okay, I'm just confirming. Thank you.
So let's work an example here. Let's say that I have a circuit and we're going to be dealing with this. Let's start in the frequency domain. So this is going to be a voltage source. Let's make this 120 angle 0 degrees. Let's call it volts. I'm going to be tricky, and I'm telling you I'm being tricky, so it's not going to be that tricky. I'm going to call, say I have an impedance here, ZA, an impedance here, ZB, and an impedance here, ZC. And let's say that ZA is 6 plus J 3 ohms. ZB is 9 minus J 8 ohms. And ZC is 12 angle 21 degrees ohms. And I want us to find the following quantities, okay? So I want us to find, in no particular order, the average power absorbed by impedance ZA the apparent power absorbed by impedance ZB the reactive power absorbed by impedance ZC. And lastly, the complex power supplied by our voltage source, Vs. So the first thing that I want to point out here, and I'm pointing this out because some of your homework problems are set up this way as well. The circuit as we are given here is in the frequency domain. However, all of our complex power relationships are carried out in the RMS phasor domain. So how do we switch from the frequency domain to the RMS phasor domain? We divide our voltages and currents by the square root of 2. Full stop, okay? So in the RMS phasor domain, this would look like 120 divided by root 2, angle 0 degrees, volts RMS. That's it. We simply divide the magnitude of the voltage by the square root of 2. We make no other changes. Here's ZA. ZB. And ZC, right? So what I am going to do, and this is what I would encourage you to do, but I can't make you do it, obviously, instead of bothering to remember equations and all of that kind of stuff, we are going to find the complex power for all of these elements, and then we're going to take from that complex power just the parts that we need to answer the questions at hand, okay? So in order to calculate the complex power absorbed by impedance ZA, we are going to need to know the RMS phasor voltage drop across VA, which I'm choosing with positive polarity on the left for no real reason, and the RMS phasor current flowing through impedance ZA, which I'm going to call IA, like so. To find the complex power absorbed by impedance ZB, I'm going to need to know the voltage drop across impedance B. So that's going to be VB, and the current flowing through impedance B, which I'm going to call IB. And similarly for C, I'm going to need the voltage drop across C and the current flowing through C. Lastly, for our source, I'm going to need the voltage drop across our source And because I want power supplied, I'm going to do the current flowing into the negative polarity terminal. IVS like so. And we are going to solve for these quantities using our standard frequency domain relationships because they're all still valid since we've just divided the magnitude of our voltage by square root of 2. Okay. So which quantity do you guys want to solve for first?
VA.
VA. Okay. So let me scroll down here. Do you want to take a crack at solving it, or do you want me to tell you how I would do it?
Well, I could start with why I made that. Sorry, let me finish writing this. Okay. I've had success in the past getting like ZEQ in the past, and then essentially solving for IA, and then that gets me VA, and then I do, in this case, I would do voltage division to get ZB or to get IB and IC, and then solve for VB and VC. That's my overall strategy.
Okay. I don't think there's anything wrong with that strategy procedurally. That being said, I believe we could be a little bit more efficient. And so let me explain what I mean by that. So if I were trying to solve for VA, I would do that using voltage division from the jump. Okay. So I could solve for VA in this particular circuit by taking my known voltage drop, which is 120 divided by the square root of 2, angle 0 degrees, volts RMS. I'm trying to find the voltage drop over impedance ZA. So that goes in my numerator. And then in the bottom, I'm going to have the total series resistance seen by my voltage source, which would be ZA plus ZB in parallel with ZC, which is just the ZEQ that you were talking about, right? So ZB in parallel with ZC is going to look like ZB times ZC over ZB plus ZC. And now I get that voltage in one step instead of 3.
Yeah, cool. Okay.
So I'm going to throw this into my calculator. I'm going to be extra lazy here. Let me scroll up. So I'm going to store ZA in my calculator as variable A. So 6 plus 3I. Store it as A. 9 minus 8I, I'm going to store as B. And 12 angle 21, I'm going to store as C. So that I'm putting in my calculator 120 over root 2 with an angle of 0 times A divided by A plus B times C over B plus C. B times C over B plus C. I get 43.649 with an angle of 18.865 degrees. Volts RMS. Just for the sake of argument, I'm storing this as X. So I'll wind up using it here in a minute. So now that we know VA, to me, it's very easy for us to solve for IA, and it's also easy for us to solve for VB and VC. So which one would you care to do?
ZB.
Okay. So VB could be written by using Kirchhoff's voltage law as our source voltage, 120 divided by √2, angle 0 degrees, volts RMS, minus VA. We could have also used voltage division, but it's overkill once we know what VA is. So I'm just going to throw this in my calculator, 120 divided by √2, angle 0 minus what I have stored as X gives me 45.778, angle negative 17.957 degrees, volts RMS, and I'm going to store this as Y. And because ZB and ZC are in parallel, DC is just VB. So now that I know all of my voltages, let's find our currents. And we can do that just by using Ohm's law, right? So IA is just going to be VA over ZA. So that's what I have stored in my calculator as X divided by what I have stored in my calculator as A. I get 6.507 with an angle of negative 7.7 degrees. I'm going to store this in my calculator just for the sake of argument as Z. IB is just going to be VB over ZB, or what I have stored in my calculator as Y, divided by what I have stored in my calculator as B. I get 3.801, or 8016, so let's round that to 802, with an angle of 23.677 degrees, amps RMS, which I'm going to store this as T. One of the reasons I prefer using my TI calculator for complex math is because I can store 8 variables. And then lastly, I'm going to have IC is just VC divided by ZC. VC is stored in my calculator as Y, so it's going to be Y over C. And I get 3.815. Angle negative 38.957. And let's use the last variable here and store this as D. All right, so we have found every voltage and current in our system. And just to be clear here, the current IVS is the exact same thing as IA. And obviously the VVS is just the voltage drop over the voltage source, right? So we don't need to do any work to find those. So we've done a lot of setup work here. Now let's get into the actual calculations that we need to carry out. So let's start with impedance ZA, okay? So the complex power absorbed by impedance ZA is going to be VA times IA conjugate. Now I do have these stored in my calculator and I can make my calculator do this operation, but I want to write things down here specifically because it's been a moment since we used the conjugate operation in this class. So I just want to refresh your memory, right? So if VA was 43.649, angle 18.865 degrees volts RMS. IA, we have up here above, 6.507. The conjugate, we're going to change the sign on the angle. So now we're going to have positive 7.7 degrees amps RMS. And when I do this math, in my calculator, that's X times the conjugate of Z. I get 284.018 angle 26.565 degrees volt amperes in polar form, and in rectangular form, this comes out to be 254.034 plus J 127.017 degrees volt ampere in rectangular form. Okay. So we were asked to find, let me scroll up here to make sure, the average power absorbed by ZA. So which of these four numbers is the average power?
The last two right here, yeah. They're just different expressions of the same thing.
So both of these are the complex power, but I want the average power. And the average power is the real part of the complex power. So that means I'm going to take the first term in the rectangular form. So PA is going to be 254.034 watts, right? So I'm doing it this way so that I don't have to memorize a bunch of equations, right? I could have done the magnitude of the voltage times the magnitude of the current times the cosine of this angle minus this angle, but I don't want to memorize a bunch of unnecessary equations, okay? So the key here is if we can calculate the complex power S, we can use S to literally find every other quantity. In polar form, we have apparent power and our power factor angle. In rectangular form, we have average power and reactive power, okay? So if we can just calculate S and take the part that we need, we can avoid memorizing a bunch of equations. We simply need to remember what the power triangle looks like. So let's try this for impedance B, okay? So SB is going to be VB times IB conjugate. So VB was 45.778 with an angle of negative 17.957 degrees. Volts RMS. IB, which I stored as T if memory serves me correctly, 3.802 with an angle of 23.677 degrees, amps RMS. Let me just double check here to make sure I stored that as T. I did. All right. Oh, but I need to conjugate this, so I put a negative sign here. I'm honestly just going to let my calculator take care of it, but some people like to do these by hand for whatever reason. So that's going to be Y times the conjugate of T. And I get 174.033 with a phase angle of negative 41.633 volt amperes. And in rectangular form, this looks like 130.074 minus J 115.621 volt amperes. So we were asked to find the apparent power. Okay. So I'm going to scroll back down here. I want you to tell me what the apparent power is, and if you need to, refer back to our power triangles.
Apparent power is 174.033.
Absolutely correct. Apparent power is the magnitude of the complex power. So it is the bit before the angle in the polar form representation. 100% correct. So our apparent power, which would have a symbol of the magnitude of SB, would be 174.033, and the units are volt amperes because we're dealing with apparent power. All right. So similar thing for impedance C, right? We would have VC, which is the same thing as VB, times IC conjugate. So that would be 45.778 with an angle of negative 17.957 degrees, volts RMS. And then IC, I stored in my calculator as T. 3.802. No, I stored in my calculator as D. I'm sorry about that. 3.815. And because we're doing the conjugate, we're going to get positive 38.957 amps RMS. So this is going to be Y times the conjugate of D, which I get to be 174.636 with an angle of 21 degrees, volt amperes. And in rectangular form, this is 163.037 plus J 62.584 volt ampere. We were asked to find the reactive power. So which of these four numbers is reactive power? Reactive power is the imaginary part of the rectangular form. So QC would be 62.584 VARs, because we're looking for reactive power. Lastly, we needed to find the complex power absorbed, or it's going to be supplied by our voltage source. So that's going to be the voltage drop across our voltage source times the complex conjugate of IA. So that would be 120 over root 2, angle 0 degrees, volts RMS, times IA. Excuse me, IA conjugate. I stored IA as Z. .507 with an angle of positive 7.7 degrees, amps RMS. I get that to be 552.124 with an angle of 7.7 degrees, volt amperes, or in rectangular form, 547.145 plus J 73.980. Volt ampere. And because we were looking for complex power, both of these representations are correct, right? So if we want the complex power, we don't need to pick this thing apart because it's the big picture thing that we were trying to solve for from the beginning. All right, so technically there are 15 minutes left of class. I didn't get quite as far today as I normally do. So there are going to be homework problems and potentially in-class assignment problems that are associated with the concept of power factor that we have not yet learned. That's going to be the first thing that I talk about on Thursday's class meeting. So I'm going to extend the due dates for the ICA and the homework for today to take into the account that we haven't covered quite all the material that I wanted to. Before we get out of here for the day, are there any further questions? All righty. Well, I hope you guys have a great rest of your afternoon, and I will see you for our last class meeting on Thursday.